Hi folks, a very good evening and thank you for joining in today. Can you please confirm if you can see my screen and also hear my audio? Let's just do a quick check if everything is working as expected before we dive into the session itself, right? So can you please confirm that? Can you please confirm that in the chat window, please? Yeah, I can see my own feed. I can also hear myself, so thankfully it seems to be working perfectly all right. Let me just all the folks who are live right now, who are already in the chat, can you see my screen and hear to my audio? Okay, that's good. Okay, good. Hey, since all of us are a little early, we'll spend let's get started at 7 p.m. sharp. Again, we're just starting early so that if there were any technical hitches or glitches, we will fix them, right? So thankfully, no glitches. You're able to see my screen and hear my audio. So let's wait for 3 more minutes and we'll start the session at 7 p.m. sharp, right? So let's just wait for others to join in. Okay, in the meantime, I could try and answer a question or two. If you have some question, please let me know. Please increase the output volume. Is there a problem with output, folks? Is there a problem that you see? Yeah, I see. I don't want to increase it too much because then it'll hurt your ears. So is this all right? Or do you want me to? So is the audio level all right? Can you please confirm that? Or do you want me to increase it? Somebody was asking me to increase the output volume. So can you please confirm? No problem. Okay, so no need to increase. Okay, no problem at all. Cool. Perfectly fine. Okay. So, okay, somebody says any resources on object-oriented design. So if you want to do low-level design, one of the books, especially for beginners, that I really like is Head First Design Patterns. This is a very nice book, very popular book also. It's called Head First Design Patterns. It teaches you a lot about design patterns and object-oriented design itself. It's a very good entry-level book. And the best part about this book is it explains concepts by taking good examples. So you'll connect, instead of learning theoretical concepts about design patterns, you'll be able to easily connect it to some real-world examples. So this is a very nice entry-level book. It covers all the basics. So if you want to get a good introduction to design patterns, Head First Design Patterns is a very good starter textbook. Will this video be available after the live session? Yes. So this is a public live session. So it will be available on YouTube even after the session is over. Okay. So don't worry about that. Okay. So, thankfully some of my teammates are also joining in. So they'll also be responding to some of the chat questions, which I may not be able to respond because of time constraints. Whether you want to use monolith or microservices, again, microservices is the way to go. So yeah, so I'll be explaining you mostly from the perspective of Docker, a little bit of microservices, but I will not be able to go too deep in this session because each of these is a big topic onto itself, right? So, okay. Is there a problem with volume, guys? I don't see any problem. Nobody's complaining except one or two folks. So if you cannot hear my audio, please increase the volume because everyone else confirms that the audio level is good, right? So if one or two of you have a problem, please try to increase your volume or just put on a headphone or a earphone, because I don't want to just increase the volume and blast. Okay, so I've increased it slightly just in case some of you have an issue, but I don't want to just blast into your ears. Okay, I've increased it slightly. I've increased the output level. So just check it now and it should be all right. Those of you some of you could reduce the volume so that it's more comfortable. Okay, so sounds good. Okay, sounds good. So let's continue with the session itself. It's already 7:01, so let's dive into the session itself. I'll also explain you how we'll proceed in this session, because this is a multi-part session. I also want to cover good chunk in each of these sessions. So let me give you an overview. I'll not be looking at the chat window now. I'll tell you when I look at it and answer the questions that students have. So this is a two-part session on how do you build a search engine or a semantic search engine when you have question and answer repositories, right? So again, this will cover both the design and code walkthrough. So we have students both from Applied AI course and the interview prep course. We'll briefly touch up, we'll spend some time on the design of how the whole system design should, what are some alternatives or what are some options we have in systems design. I'll also walk you through each of the code snippets, and let's do it step by step. Again, we will not be able to finish this in one session. Today is the first session from 7 to 8:30 p.m. Tomorrow is the second session, right? So from 7 to 8:30 p.m. again. So the way we'll operate is today in both these sessions, I will cover the concepts from 7 to 8 p.m. I have an alarm set on my phone at 8 p.m. So I'll stop explaining the concepts at sharp 8 p.m. right? So we'll spend roughly 60 minutes in understanding a bunch of concepts. Till wherever we cover, whatever concept we are covering at 8 p.m., we'll just finish it and close it. Then we'll spend 30 minutes wherein I'll pick questions from the chat window and try and answer as many as possible. Again, please understand that since this is an open session, we will not be able to answer every question. Tomorrow also, we'll repeat the same thing. 60 minutes, I'll cover the concepts. 30 minutes will be a question answer session. This way, in 60 minutes, we get ample time to cover a good chunk of stuff. And most questions you have will be covered in the sessions. Anything that is not covered in the sessions, we'll do a discussion for 30 minutes. This is how we'll cover both today's session and tomorrow's session, right? So, okay, so let's go into the agenda. So first I'll explain you the prerequisites. Then I'll explain you what is a problem definition and what are the requirements that we want or what are the constraints that we have in designing the solution, right? So the problem itself and also what do we want out of the solution. Then we'll go into the data set. I'll show you a very popular publicly available data set. I'll also do a quick code walkthrough on how to pre-process this data set and common mistakes that people commit when they're doing this simple pre-processing. Okay, number one. Again, we'll just get some high-level numbers, just reading the data set, understanding what's there in the data set, right? Nothing too fancy here. Next, we will go and understand the high-level design and the data structures that we need, right? So this is a fairly important chunk, both for our interview prep students and for AI students, right? So here we will touch upon multiple options you have for high-level design. Actually, in reality, oftentimes there is no one right design, right? So there are multiple right designs based on the constraints you have, based on options you have. And we'll also touch upon some interesting data structures which are important in the context of this problem. Next, we will understand about containerization, especially using Docker. Again, those of you who don't know some of these concepts, it's okay. I'll try to explain them intuitively from first principles. I only assume you know the prerequisites. So don't worry if you don't know what is Docker or what is containerization. I'll explain you everything. Then I'll show you a bunch of commands on how to set up Docker on your own computer, whether it's Windows, Mac or Linux. And I'll just walk you through it, how to set up the whole Docker containerization framework, right? So again, we'll also understand why we are using Docker. Again, whenever we explain a concept, it's very important to understand why we are using it in the first place. So if you don't know these concepts, it's okay. I'll explain them from scratch. Next, we'll learn about sentence vectors. Some of you who know machine learning and deep learning might already know what a sentence vector is, but there might be others who don't know, especially software engineers who don't know what is a sentence vector. So I'll give you a brief overview without going too deep into the mathematics of it. I'll give you an overview of what these sentence vectors are and some basic mathematical understanding of it, and we'll also write some code to understand sentence vectors. Cool. Next, we will set up Elasticsearch, which is a very, very popular search platform, or it's one of the very, very popular inverted indices based data store. I'll explain you all that when we understand some data structures. I'll explain you how to install Elasticsearch itself, how to set up the whole Elasticsearch on Docker. Next, we'll learn how to index the data. Again, here I'll walk you through some slightly lengthy code, not too long, but very interesting code. Then we'll touch upon how to search, given that you've already indexed or you've added the data to your Elasticsearch. How do you now perform the semantic search, both using sentence vectors and keyword-based search? Then we'll touch upon how to deploy this whole system, wherein I'll walk you through code and some pointers. At the end, I'll discuss some extensions to this solution, because again, remember that this solution that we are explaining is mostly for educational purpose. While we try and give you multiple options, the objective is to keep it simple enough so that we can cover it in 2 1.5 hour sessions. So we'll discuss about some extensions, and I'll also give you an optional assignment that those of you who are interested can perform, so that this is like an extension to what we have done in these sessions, right? So that you can dig deeper and understand this better, right? It's an optional thing. You're most welcome to do it. Today, again, we will not be able to cover all of these 11 points. We'll try to cover as many as possible today. We'll stop at sharp 8 p.m. and tomorrow we'll continue where we left off. Okay. Again, there are a bunch of references here, so don't worry about taking notes. I'll share these slides or notes at the end of the discussion. I'll share these slides and notes at the end of discussion today and tomorrow. All the code that I'm walking through, I'll also share it today after the session and also tomorrow after the session. Okay, these are some very nice simple references. There's a very nice blog from the Elasticsearch company itself on how to do text similarity using vectors and things like that. There is also a very nice code repository that they refer to in this blog. Also, if you don't know some basic terms in Elasticsearch, this is a very nice reference, wherein if you know standard databases, because I'm assuming all of you know some SQL to some extent, you don't have to be an expert in SQL. I'm assuming you know the basics. What is a table? What is a database? What is search? What is querying and things like that, right? So if you want to relate some of the terms that you learn in typical relational databases, RDBMS, you can use this list of terms and their definitions. It's a glossary. Also, there is a very nice simple tutorial on using Python with Elasticsearch. It's a very nice blog from Naukri's engineering team, the data science and engineering team. It's a very simple blog. The reason I'm pointing to this blog is because it's written very nicely, elegantly, and simply, right? So some references here. I'll keep pointing you to more references as we progress through the sessions. Okay, so let's go step by step. First and foremost, what are the prerequisites? Most important prerequisites is that you know basics of Python programming, some basic Python programming. And if you know Unix commands, that's good. If you don't know, anyway, I'll explain each of the commands, Unix/Linux commands, right? Like how do you create a directory? How do you go into a directory? If you don't know some of these commands, that's okay. I'll explain most of them, but if you know that, it will be easier. Again, please understand that since this is a public session, there will be students across a wide spectrum of skills and knowledge. So we'll try and ensure that we can help even students who are not that advanced can also understand. Some of you who are advanced students might feel little dull in between because it feels like little repetitive for you. But we also have to understand that there are some students in the beginner who are at a beginner level to whom we will try and explain clearly, right? We also assume that you know the basic inbuilt data structures in Python. You know what is a list, you know what is a dictionary or a hash table, you know what is a tuple, what is a set, some basic stuff. Again, please understand that we will not be able to dive deep into all the concepts. I'll try to, because Elasticsearch itself, I mean, we can do a 50-hour session, 50 hours worth of content just on Elasticsearch, right? Sentence vectors itself could be like some 30-40 hours of worth of content. So we will not be able to dive deep into all the concepts, but I'll try to give you intuitive understanding of the concepts so that you know how things fit together. And I'll give you extra pointers wherever you can study after the sessions, right? So please understand that we'll not be able to go too deep, and we are trying to also help students across a broad spectrum of skills understand. Cool. So, okay, now let's see. Okay, so let's understand the problem definition itself. So if you go to Stack Overflow, I've just taken a screenshot from Stack Overflow itself. I just searched here. I just said how to install pip. Okay, Stack Overflow. I just said how to install pip. This is the question that I have. The moment I ask this query or question, it gives me a bunch of answers. If you notice, this question is very similar to the question that I've asked. This question is also very similar to this. This question is also very similar to this. So our problem definition is, given a question like this, can you find similar questions in a repository of question and answers that we have? A good example is Stack Overflow. We'll also be using some publicly available data from Stack Overflow itself for this session. So if you notice, the data that you have here is QI. I is basically the numeric. So this could be Q1, Q2, Q3, so on and so forth. So you might be sitting on hundreds of thousands or even millions of questions. Okay, let's assume every question is represented as QI. Now, given this question 1, each question can have multiple answers. Right? Remember that each question could have multiple valid answers. Right? So for question QI, you have AI1, which is the first answer to this question. Then you have the second answer, the kth answer. So your data set itself, the data set that you have is basically a huge repository of hundreds of thousands or even millions of questions. Okay, you have a clearly described question and multiple answers provided by many people. Okay, again, this is one setup. There could be many other setups. You could have a setup. Imagine if you're running, if this is data coming from some company's customer service, then you might have question I and just answer I. One answer for this question. So you could also have that setup. Okay, this is a more generic setup, right? Another very important thing here is the results that you get. You should order them based on relevance. If you notice this says, given this question, it will try to come up with answers based on relevance. We want most relevant answers given this question, right? That's very, very important. Relevance again is subjective to some extent, because here it says how to install pip. It says how to install pip on Windows, how to install pip with Python 3, how to install packages using pip according to requirements.txt file from a local directory. Bunch of questions here. So what we want is, given a question like this, we want a sorted or ordered list. We want to give an ordered list of answers, with the first one being the most relevant, ideally. Okay, that's very important. So ordering of related questions is important. Next, it has to be very, very fast. Okay, nobody will give you a search query and expect to wait for a few minutes. Typically, it should happen in under half a second or roughly about 500 milliseconds. Right? The smaller, the better. That's very, very important. Imagine if you're an engineer at Stack Overflow or a machine learning guy, when you're designing a system like this, speed is extremely important. Right? I'm just explaining you the problem definition, the data sets that we have. How do we want the results to be? What are the engineering constraints that we have? We want it to be fast. Remember, the moment you want it to be fast, you can't use some complex models or complex architectures. You want your systems, you want to use very efficient data structures. You want to also make it super fast and scalable. I'll come to scalability in a while. Next, very importantly, we want it to be high precision and high recall. Now, some of you who are non-data science folks may not understand what is high precision and what is high recall. High precision basically means, imagine this is the question that I ask. Let's assume Q star is the question that we are asking, right? And my system that I've built, let's assume gives Q1 as the first result and Q2 as the second result, and so on and so forth. We want, given this question, we want these results to be very relevant or highly precise given this question. That's very important. We also want it to be high recall. What do we mean by recall here? Again, there are specialized metrics in search that I'm not going into. There are some special metrics called NDCG, etc., which are often used by search engine companies. I'm not going into too much detail here, but this is one topic if you're interested. This is one way to measure how well your search engine is doing. But we're not going to go into very advanced stuff here, because just to explain what NDCG is will take considerable amount of time. Now, the other thing is recall. What does recall mean? Imagine if the question that we are asking is Q star. If there is a question 10 which is relevant to question Q star, then Q10 should be there in the results in one of the top positions. Okay, we want to be able to recall a very relevant question given this question Q star, that is a query question, right? That's important. And all the results that our search engine gives, they should be, the precision here basically means that most of the results that we have are very relevant to this question. And in my whole repository of hundreds of thousands or millions of questions, if there is one question which is very relevant to Q star, we want to be there, we want it to be there very high in the search results. Okay, this is again, I'm just giving you intuitive understanding of what precision and recall are. These are very specific terms in machine learning. Since some of you may not know these in-depth machine learning concepts, that's why I'm just giving you intuitive definitions here. Second, we want the computational or the server cost to be low. Now imagine any company wants to spend as little money as possible on the servers, right? So when you want your server costs to be low, there are three major things. Again, there are more things that you need to worry about. There are three things that you should worry about. One is, how many queries will you get per second? Of course, a large website like Stack Overflow might get thousands of queries, thousands of questions being asked every second, right? So what is your, how many queries, how many search queries are done per second? That's a very important thing. This will define the architecture that you have to some extent. This will also define, again, remember, you want the system to be fast. You want the system to respond in less than 500 milliseconds. That's one part. But you want your system, you could say, we want our system to also handle 1000 queries per second, right? So this is basically volume. So 1000 QPS basically means that it's going to see 1000 queries per second. So this is speed, this is volume. Now, if you have large volume, then you might require more servers. More servers, more cost. And what is the cost per server? Again, if you're hosting your solution on some cloud-based system or your in-house servers, the more complex the server is, imagine if the server requires 64 GB of RAM, right? That would, versus, suppose there are two architectures. One requires 64 GB of RAM, other requires 8 GB of RAM. Obviously, an architecture that requires fewer or smaller amount of RAM is always preferable because the server cost will be less, right? So all these are real world constraints that will play a very important role in your architecture design. Okay, I'm just giving you hints at how to think when you're actually building a system of your own, right? Very importantly, you want to be able to build and deploy a system, at least a basic version, if not a very advanced version. You want to be able to build it in a week's time. Again, this is not exactly an operational metric, but this is something like, okay, we want to build a search engine. How quickly can we build it? Can we build it in 1 week? What you build in a week need not be a very advanced solution. It could be a basic first cut version. So can you build a basic first cut version in about a week with 1 or 2 engineers or data scientists, right? So again, this is also an important constraint that many people don't take into consideration, right? So our problem is very simple. We want to build a simple search given a repository of questions and their answers. We want it to be fast. We want it to be high precision, high recall. We want as low server costs as possible. We want it to handle as many queries as possible per second. We want the cost to be low. We should be able to build and deploy it in under a week with 1 or 2 people. Again, all these are real world engineering constraints. Now let's look at the data set. Okay, so we understood what we have to build. Now let's go into the data set itself. So there are multiple publicly available data sets. The one that I picked up for this session is Stack Sample. Okay, so this data set is available on Kaggle, and let me just walk you through. So let me just walk you through it. Okay, so this is the Stack Sample data set. So it says it's a good sample of data from Stack Overflow. The compressed file itself is roughly 3 GB, so it will take some time for you to download the whole thing. So it says dataset with text of 10% of questions and answers from Stack Overflow, programming, Q&A, website, etc., etc., etc. So when you download this data, you get questions, you get a file called questions, answers, and tags. Okay, so I'll explain. We'll understand this data in brief in a while. but this is where you have to download the whole data, right? So now once you download the data, of course, if you just click on this download button, it will give you a zipped file dot zip. And how do you unzip it in, I mean, of course, you can use an unzip program like tar or untar. But if you're using a Unix or a Linux or a Mac based system, you can just say unzip and the name of the file, right? So if you just do unzip name of the file, let me show you my terminal that I have here. Okay, so so all I have done here is I've just I'll show you these commands again in the context of Docker little later, but all I've done here is I've gone to this link. I've simply downloaded the data from here, the 3 GB of data, unzipped it. I mean, you can use any tool of your choice. I just prefer to do it command line personally. So I just type unzip, whatever is the name of the file .zip. Now what we want to understand here is how many questions are there, how many answers are there, what are the fields, what is the data, etc. For that we have a simple Python script called as readdata.py. Okay, so let's go through the readdata.py. So again, I prefer using, so again, I'll share all of this code with you in a while. So this is the code snippet. I'll walk you through this line by line. Again, those of you who do not know Linux, so this is my Linux. Okay, this is my Linux terminal. Okay, let me just tell you, I forgot to mention that. This is my Linux terminal. Again, Linux is what is used extensively for all major servers, right, in the world. It is the most popular operating system for servers, right? So this is your Linux terminal. It's just like your command prompt on Windows or terminal on Mac. Those of you who use Windows and Mac. Again, Mac is mostly a Unix at its very core. So if I want to see, suppose ls-lrt, or you just say ls, that's okay. So if you just say ls basically in Unix or Linux based systems basically means list. It lists all the files and folders that you have. So here we have a folder called data. We have a file called indexes.py. We have something called as install.sh, readdata.py, testuse4.py. Okay, we'll explain each of these eventually, right? By tomorrow end of day, by tomorrow's session end, I'll explain all of that. So what we have done here is, so cd data. cd basically means change directory. Those of you who don't know Unix, right? So I've gone into the data. So if I just type ls-lrt, so ls-lrt will give me much more detailed view, right, of, it's basically listing. So this command is a list command with some more parameters that I'm giving here. So what it tells me is that this data folder has 3 files: answers.csv, questions.csv, tags.csv. So this is nothing but what I have done here is I've downloaded this data, unzipped it and put it into a folder called data. That's all I've done till now. Okay. Now if you see answers.csv, look at the file size here. Okay, this is the number of bytes that are there in answers.csv. Similarly, questions.csv, tags.csv. Now, if you want to edit anything in the command terminal, again, my favorite editor is Vim, right? So Vim is basically an editor that you get in the Linux or Unix terminal itself. So if you say Vim, okay, so we are in data. So cd ... basically means go back to the parent directory. Okay, cd ... basically means go back to the parent directory. Again, I'll keep explaining you these Unix commands if you're not comfortable with them. So just say vim read data. Vim basically is like a editor that you get inbuilt in Unix terminal, right? So let's go into it. Let me walk you through each of these lines of code. Okay, remember that you have the questions.csv, you have the questions.csv, you have the answers.csv, right, and you have tags.csv, right? Of course, you can find some of the information about them from the Kaggle description itself. So this says, okay, if you go here, so if you go here, it says questions.csv contains title, body, creation date, closed date, whenever this question was closed, score, higher the score, more important or more liked the question is, and who is the owner, and some meta information, right? Similarly, answers. The answers.csv contains so here the questions also contains the title of the question, the body of the question, etc. I'll explain you these one by one. So these are the three CSV files. Now if you go back to our code, let's just understand how many rows we have in questions, how many rows we have in answers. So we are trying to just understand how many, it's a very simple Python code, nothing fancy. Given that you know some Python, this should be straightforward. Again, I'm just importing CSV, which is a very popular module to process comma separated value files, right? Again, here, please note that I'm not using pandas to load the data. So there are two approaches here to understand this. One, the data science guys typically tend to use the pandas library here, but remember that this data is large. Because this data is large, if you try to read the whole questions.csv and store it as a data frame in pandas, at the same time read whole of answers.csv and store it in a data frame, the memory consumption will be huge. Actually, I tried that. It almost consumed close to 5 GB of RAM just to load, I think almost 5.5 GB of RAM just to load questions.csv and answers.csv into data frames. So instead of using pandas in a problem like this, a very common mistake that the data science folks do for simple tasks like this is to use pandas because they're comfortable with it. But instead of doing that, it is preferable to use the CSV module because look at the code here. Again, this code is very simple, easy to understand. Okay, so we are saying count equals to 0 with open. Again, we are opening the questions.csv and we are saying the encoding in this is Latin 1. Okay, again, you can read about encodings, whether you have Unicode encoding, ASCII encoding, etc. Latin 1 is very popularly used, and I have found out that this data set is in Latin 1 encoding by reading some of the comments and some of the code snippets and kernels for this data set. So if you look at this data set, so stack sample, there are a lot of kernels where people have published some simple code snippets, and if you don't give this, if you don't give Latin 1, there will be some encoding problems. So what we are saying here is just open this file, okay, questions.csv as CSV file, and then we are creating this read CSV as a CSV reader. Look at this, all that we are saying here is, this is our CSV file, right? We are calling csv.reader and we are giving this file here, and we are saying the delimiter between different columns of data is a comma, because it's a comma separated value file, right? So what happens if you have your first, so if this is your whole data, how does CSVs work? If you have, let's say 1AB, 2BC, etc., etc., how is it written? In the first row, you get 1, A, B. In the second row, you get 2, B, C, and so on and so forth. Of course, you could also have a header which says, okay, that this is an ID, this is a name, right? And this is some address or something like that, right? So this is called the header of a CSV file, which tells you what each column represents. And then each of these values in a table, this is how you can imagine this as a table, but the way it's stored in the file is comma separated values. That's what CSV file basically means. So first and foremost, we are saying read CSV, and then we are saying next. Because the moment we say next, what happens is it will skip the header. So if you just go here, let me show you how this looks like. Okay, so let me quit this. Okay, so there is this command called head. Okay, head data questions. Head basically prints the first 10 lines, right, that you have in this file. Okay, so if you notice some amount of text that it's printing, where is this? Okay, so if you see the first line here, the first line contains ID, the owner user ID, creation date, closed date, score, title, body. Look at all the fields that are there. So this first row is often referred to as the header row, which lists all the names of each of the columns. So the first one is a unique ID given to each question. The second one says who asked this question. Okay, so the owner user ID, it's a unique ID given to each user who owns this question or who asked this question. Then at what timestamp was this question created? What timestamp this question was closed because the user who asked that question got the answer that they were expecting. Score is a measure which implies roughly, approximately, how popular this question is, how many people upvoted it. Then you have title, which is basically the title of the question and the body of the question. Now you might wonder what is title and what is body. So if you go to Stack Overflow, So if you just go to Stack Overflow here, just go to Stack Overflow, pick any question. Okay. So just ask any question. If you go here, so this is called the title. This is called the title, right? So this is the title. This is the body of the question. Okay. So there is a title, there is a body, and there are other answers that people have given. This answer is the most popular answer. This is also the accepted answer, right? So title only captures this short description of the question. This body captures the more detailed description of the question, right? So that's what we have. So the title and body. Now, if you notice the first row here basically has the header. So we want to skip the header because header doesn't contain data. It only contains, it only contains the column names. So by doing next, what we are saying here is skip the first row, go to the next row. Next, if you notice here, this is a very simple for loop. What does it say? For row in read CSV, which means this read CSV is like a iterator, right? So I can iterate on read CSV, reading each of the rows. And as long as I'm reading these rows, I'm just incrementing my count. Simple. Now, finally, I'm just going to print. I'm going to say number of rows that we have and length of row. Remember, a row represents all of the elements that are there in that row. Again, we have already mentioned that the delimiter is comma, so it will be processed accordingly. So when we print this, when we print count comma length of row, what we get here is it says how many rows you have and how many columns you have in the questions.csv. The code that we have for questions.csv, same code for answers.csv also. It's the same code. Initialize count to 0, open answers.csv, just read CSV, skip the header. Look at this, skip the header, skip the first row. Then this for loop basically tells you to go through each of the rows and keep incrementing the count and print it finally. Now, if you execute this code, right? Again, I'm using Python 3.6 here. Okay, I'm using Python 3.6. If Python 3.6 read data.py, it will take a couple of minutes, but it will answer us in a while. Just give it some time, it will come up with the answer. But I've already executed it earlier, and this is what I get. I think -1. Okay, let's just wait. Again, because the most important part, again, we can just skip this because I've already executed it in the past. The most important lesson here is please try to use, okay, so if you have written this code not by reading the CSV files line by line, but imagine if you wrote the code using pandas, right? If you try to load all of this into one data frame 1, and all of this into data frame 2, the memory consumption would be huge. Right now, what's happening here is it is going to read from this file, right? Line by line, process it and just dump it from memory. I'll show you a little later how much memory this consumes. If you have written the same code using pandas, it was easily consuming almost 5+ GB of RAM. Okay, this consumes less than 200 MB of RAM, right? So it's very important as a software engineer, even as a data scientist, to be careful of memory consumption. Because remember, one of the constraints that we have is we want to keep our costs low. Look at the business constraints that we have, or the specification requirements that we have. Look at this. We want low computational server cost, right? We want per server cost to be low, which means we want to consume less RAM. Let's not forget that basic stuff. Okay, cool. So okay, so this code, if you just execute it, the answer that you'll get is okay. I have the answer here. I've made a note of it. I think it is 1 less than this. I think roughly these numbers. So the questions, so if I just execute Python 3.6 read data.py, it gives this. This is basically 1.26 million. Look at this, roughly 1.26 million questions, and each question has 7 columns in the CSV file. And the number of answers here is 2.01. So roughly 2.01 million answers. Each answer has 6 columns. Now let's look at what does the answers CSV has, right? So let's just do head data answers.csv, right? Again, head prints the first few lines. Now if you notice here, the first one it has is an ID given to each answer. Who answered that question, right? When was the answer created? What is a parent ID? Parent ID basically means, so look at this. If you have question I and you have some other answer, let's just call it AJ. So AJ's parent ID will be the ID of the question for which this is an answer. So using this parent ID, given any answer, you can connect it back to the question that is related to. Similarly, you have a score, which is basically a measure of how many people upvoted it, and you have body here. Right? So body basically means what is the text that is there in the answer. So the parent ID is a very important field which tells us given an answer to which question it is an answer to. Right? So that's important. So it has 6 columns, 1, 2, 3, 4, 5, 6. ID, user ID, creation date, parent ID, score and body. So that's what if you execute the read data, it's a very simple code. The reason I showed the code is to help you understand that writing efficient code is very important skill, especially in production environments. Okay, cool. So again, I'll share all of this code with you. It's very simple. I mean, you can write it yourself. It's not rocket science. Okay. Okay, so we have gotten some understanding of the questions.csv, answers.csv. We are ignoring the tags.csv for now because we are building a first cut solution. I'll tell you in the extensions how you can also use tags.csv later. Okay, so now given that we understood the data, let's go into the high level design. Okay, so this high level design and data structures, I'll explain you how to think about this problem and how can we handle this whole solution. Again, it's very, very important before you write your code for the whole solution to understand what data structures you need and what is a high level design itself. This is extremely important because if you mess this up and if the design that you have is not appropriate for the requirements that you are trying to solve, your whole system goes for a toss. Okay, remember that every question QI, there are multiple fields here. What we mostly care about is ID, title and body. Right? That's what we care about, because to given any question Q star that a user asks in the search bar, this is your search bar, right? Given any, again, I'll keep using Q star to represent a question that a user asks, QI to represent a question that is already been asked, which is part of a data set. So I'll keep using QI to represent the ith question in our database. I'll use Q star as a question that the question being asked. So to find given Q star, to find the appropriate question QIs from our data store, the most important fields are title and body. Those are the two most important fields. Similarly, given any answer, the most important fields are the answer itself and the parent ID, because the parent ID helps us connect back to the question that it's an answer to. Now, there are multiple design choices that we have now. Okay, you can say, I will only search whenever a user asks for a question. I will only search in the titles of all the questions that I have in my data store. Again, this is your data store. I'll only search in the titles. Again, this is the simplest solution that we will explain in this session, but you can easily extend it to searching both in the title and the body. Because typically the way Stack Overflow works is the title is a good summary of the question that a person has asked. Body is a more detailed explanation of the question, right? So most things that people ask in the search bar, most questions that people ask will be short, right? So whenever somebody asks a short query here, it makes a lot of logical sense to only search in the title, right? To only use title data. But of course, it's a design choice that you have. But you could say, okay, I not only want to search in the titles of all the questions I have in the data store, but I also want to search in the body. So this is the simplest because it will be less amount of data and it will be fast. It will be the simplest solution. But you have design choices. You can say, I'll just try with titles of all the questions that I have in the data store, or you can say, I'll use both title and body. I'll search whatever question is to, whenever somebody asks a question, I'll search both in the title and body. That's a design choice that you have. In the real world, you have to test by just building something with titles first, see how well it works. If it doesn't work very well, then you have to also concatenate the body and see how well the whole system works. If that also doesn't work, take all the answers that are there for the given question, concatenate that and take this whole data to see if you're getting more appropriate answers. There is no one right answer here. It is something that depends on the problem that you have, and you have to try. These are design choices. Whenever you have multiple design choices, you should always start with something simple. So what we'll do now is we will be using only the titles of each question QI to search for the most similar title given a question that somebody asks, which is Q star. Okay, that's a design choice that we are making because we want to build a simple solution first. But the solution that I'll explain step by step along with code is very simple to extend it to both the question body and the answer bodies. Okay, but these are important design choices that you have to be aware of. Next, look at this. Okay, so let's take this. You have QI title. So question I is title, because we said we'll only bother about titles now. This title is basically a sequence of words. This is word 1 in question I's title, word 2 in question I's title, word 3 in question I title, so on and so forth. It's basically a sequence of words. Now remember, what we have is a search problem. Always remember, this Q star is basically a sequence of words that somebody is querying. Right? That's what you have, right? This is your whole data store where you have QIs, the titles of QI, let's say Q1, Q2, right? So on and so forth. You have multiple questions here. When you ask this, you want to find the most relevant questions from here and return. It's a search problem. The moment you see a search problem, the first thing that should strike to you, the data structure that should strike to you is a hash table, right? Logically thinking, is a hash table, because hash table has an order of 1 search, right? It's the fastest search that we know of. Obviously, it's like no brainer there. But the question here is, how will you design a hashing system? Okay, the simple hash, in any hashing or dictionary, hashing is the general mathematical concept. What we have in Python, hashing is implemented using dictionaries in Python, right? So whenever you define a dictionary, you have to know what are the keys and values. So given this problem, how will you define these keys and values? That's an important thing that you have to think through. Again, fundamental knowledge of data structures and algorithms is extremely important to solve real world problems. Many people don't realize it, but it's important. Okay, so the standard hashing based technique using keys and values may not work very well for this. So there is a specialized data structure called as inverted index. The way inverted index works is as follows. Okay, imagine we have a bunch of questions. It's a very simple strategy. Imagine you have question 1, question 2, so on and so forth, some question 1 million. Okay, you have 1 million questions. Again, we are only looking at titles, we are ignoring everything else because we are trying to build the simplest solution. Let's assume Q1 has the word pip. Okay, Q1 also has the word off. Q1 has some title which contains multiple words. It also contains pip and off. Okay, Q2 contains some words, Q3 contains some words, so on and so forth. Q1 million contains some words. Now, to find all the questions, again, remember what are we given here? We are given Q star. Q star consists of some words. Okay, let's call it W star 1, W star 2, W star 3 and W star 4. Let's just call it this. So given this sequence of words, we want to find those questions which are most relevant to this. How do we find it? Now think about it. What if we pre-process this whole data and build an inverted index as follows? The way we build an inverted index is as follows. Take every word here. Let's take the word pip. Make this word pip a key. Again, what you have here is a fancy, there are multiple implementations of inverted index. I'll try to explain the simplest one. So pip becomes the key now. And in the value, what you have here is, in the value you have the document number and the number of times pip occurs in this, not document number. Document is a term that's used in Elasticsearch, so I'm using it. But so what we have here is the question number and the number of times the word pip exists in this question. So for example, imagine pip occurs twice in this whole question. Okay, so what we'll do here is, we create a key called pip and we say, since pip occurs twice in Q1, we'll create an entry here. Again, this will be your whole values. This is your key, this is your values. Okay, you can design it like a linked list. You can design it whatever way you want. That's not rocket science. It should be straightforward. Or you can just put it in a list. Just put it in a Python list if you want, right? So because pip occurs twice here, we are storing this information that pip occurs in question 1 2 times. Similarly, let's assume Q2 pip does not occur. So we don't store Q2 here. Let's assume in Q4 pip also occurs once. So we store that information. So we are constructing this index. This is also often referred to as inverted index. There are multiple ways of storing complex inverted indices. I'm explaining the most simple way to understand it. Similarly, let's assume question 46 has the word pip occurring once. Question 32 has it occurring 3 times. Question 61 has it occurring once. Let's just say. Okay. We also store some other additional information here saying how many questions does the word pip occur in? It occurs in 5 questions. Again, you can think intuitively. There is one more term that I want to introduce you to. So each of these questions can be thought of as a document, right? Document is a standard terminology that is used in search. So you're given a search query. This is what is called search query, which consists of words, also called as keywords. And you're trying to find those documents which are most relevant to this search query. So document here in our context basically means your each question's title, right? So that's one way to imagine it. Now, what are we storing here? So the moment, okay, so the important question here is, imagine in the Q star, there is some word pip here. Now we want to find all the documents in which pip occurs. What do? You take this word, you just hash this, it will automatically, because hashing is order of one time algorithm, it will automatically tell you all the questions in which in which the word pip occurs, right? Similarly, you create for all the words, for all the millions and millions of words that you have in this huge repository of 1 million questions that you have, for every word you create an entry and you create a list of all the documents or all the questions in which this word occurs along with the frequency or the number of times this word occurs. Also, you store the number of documents containing this term. Now, in this whole setup, again, this setup is very important. This number represents the number of occurrences of this word pip in this question Q32. This final number in red basically represents the number of documents containing this term. Remember, a word like off will occur many times. Okay, if your questions are lengthy, it will occur many times in your documents or questions. Now, the fun part here is this. The power of inverted index is this. If somebody asks a question, right? So, sorry, if somebody asks a question Q star, you can very quickly, let me change it. If somebody asks a question Q star, which has W star 1, W star 2, W star 3, W star 4, 4 words. So you just use this word, do a hash, you will find, let's assume that word occurs here. You can get the list of all the documents and how many times this word occurs in each of these documents very quickly. Now, the number of words in a question or a search query will be small. Nobody will type like 100 words here. People will type very few words here. So if there are K words here, you can get the list of all the documents that contain these words in order of K time, because the search itself is order of 1. So this is called the inverted index because we are constructing an index with the words as the keys and the document numbers and the frequency of this word occurring in the document or the question numbers as our values. So we are inverting the concept of a typical index. Okay. So now, okay, so this is how we can construct it. Again, you can implement inverted index on your own. It's not rocket science. But at the end of it, let's look at this. If you have Q star, which has, let's say, K words, you can say Q1, Q4, Q5, all these are questions or documents which contain this word. These are all the documents that you have which contain W2 and so on and so forth. Then you can create a big set called S, which will contain all the documents. See, S is basically a union of all of them. Now in S you will say, okay, Q1 is could be a relevant document or a relevant question to this Q star because both Q1 and Q star have the same word W1. Similarly, Q7 could also be a relevant document because Q star has W2 star and Q7 also has W2 star. So you create this set S of all the potential relevant documents. Again, what are we doing here? Till now, what we are doing here is keyword based. We are just we have built our whole inverted index using keywords. And what are we trying to do? We are trying to get a list. Again, remember, in typical search, there will be millions of documents, even billions in some cases like Google. This search is extremely fast using inverted indices, right? Now, given these documents, the next big question here is which of these documents are relevant? How do I order them? Remember, search, what you want is an ordered list of relevant questions. What you have here is a set. You don't have a list of relevant documents. Now, how do you design something which is a list of relevant documents? So you have to come up with something called as a scoring function, also called as similarity function in mathematics or in machine learning. What this scoring function does is, given any qi, remember, look at this, for all qi that belong to this set S, we just constructed the set S, right? So take the set S, let's assume the set S has a bunch of, let's say, 100 questions, 100 relevant questions which have the same keywords as q star. Now what you want to build is, you want to build a scoring function which says how relevant is q star, or how closely related is q star to qi, or in other words, how relevant is qi to q star. If you can come up with a scoring function to do that, a very simple scoring function if you can come up with. And again, remember, the scoring function has to be fast, because you want, again, if you have 100 documents here, right, you have to be able to compute this scoring function very, very, very fast. How do you do that? So there are many scoring functions in natural language processing and machine learning. The simplest one is called TF-IDF. Okay, it's one of the simplest ones. It's also used in Elasticsearch as a basic simple stuff. Again, you can write your own scoring function and make it work. The simplest one is called TF-IDF. Again, I'll not be able to explain the whole concept of TF-IDF because that would take a lot of time. I'll give you an intuition for those of you who don't know machine learning, the intuition behind TF and IDF. So what TF and IDF says here is, we'll compute two terms and multiply both the two terms. So first thing that we'll compute here is TF. TF basically says, okay, look at this. It basically says how many times a word occurs. So look at this. You have a bunch of documents here. Look at this. You have a bunch of documents or a bunch of questions, right? So TF-IDF based method basically says, if a word occurs more times, like for example, in our case, let's take this example, right? So in this case, because the word pip occurs more times here, Q32 may be more relevant to a question which has pip as one of the keywords in the search query, because it occurs more times. That's important, right? Similarly, IDF basically captures the notion that there will be some words like of, the, if, and of, and but. There will be some words like these. These words occur in all the documents, right? So these words occur in all of the documents or all of the questions in a data set. So we want to give less importance to these type of words, and we want to give more importance to words which occur in fewer number of documents. Remember, in the data structure that I just stored here, in each document, how many times the word pip occurs. This is helpful in computing the term frequency. Amongst all the documents you have, how many documents does the word pip occur? Pip occurs only in, let's say, 5 documents. But the word of, let's assume, occurs in 68 documents or 68 questions. Because of is such a common word which occurs in so many documents, we want to give less importance to words like of and more importance to words like pip when you are computing the relevance or the similarity between a question q star that you have and the question qi that you want to compute the similarity to. Again, please understand that I have simplified the concept of TF-IDF a lot. There is a lot of very interesting mathematics behind it. In our AI course, we almost spend, I think, 30 to 40 minutes just explaining how TF-IDF works internally, the mathematics behind it, with almost 1 more hour explaining related techniques, right? So we'll not be able to go into that depth today, but I'm just trying to give you an intuition. So what this will eventually result in is, it will compute the similarity between your search question or your query question and each of the questions that you got in your set S. Now, Finally, when you have to order the results, it will order based on this similarity score. It will simply say, okay, is Q star, so let's assume you computed the score for Q star versus all the documents that you have in S. Let's assume Q star comma Q4, the score is highest. Then in the search results, Q4 will be the first. Let's assume after that Q star, the score between Q star and Q10 is highest. Then it'll have Q10 as a second result and so on and so forth. Again, TF-IDF is extremely fast to compute, and hence many libraries which implement inverted indices like Elasticsearch use it as a default methodology to rank. Again, remember, speed is also extremely important. That's why we have stored this additional information on how many times the word or the keyword occurs in each of these documents, in how many documents this word occurs in, right? So that's the important part. Now you might say, okay, let's implement this whole thing. Cool, right? So we know how to implement it. Again, if you're a non-machine learning guy, you might have to understand how TF-IDF itself works, but it's very simple, right? If you're again, in implementation of problems like this, you typically have one data science guy and one software engineer, or a data science guy who knows software engineering, or a software engineering guy who knows data science type of people, right? So now in this system, if you notice, you can implement an inverted index. It's not rocket science. You should be able to implement it using dictionaries and Python. It will take you some time, but it's not rocket science. You can implement set union because sets is an inbuilt data structure in Python. You can implement TF-IDF based scoring, and you can implement this whole thing on your own. But in practice, very often what happens is, because one of our requirements, look at the business requirements that we have. One of our requirements is to be able to build and deploy a basic version in a very short amount of time. If you start implementing all the data structures on your own, it might take more time. So a very good solution in such a case is just look in open source community, what is the best implementation that you have. So one of the best implementations of inverted indices is a NoSQL database, very popular one called Elasticsearch. What Elasticsearch does is it implements an inverted index. It does scoring for you using a TF-IDF based mechanism, but it also gives you the flexibility to write your own scoring function if you want. It's distributed. Okay, you can run Elasticsearch across multiple nodes. Again, why is that important? Imagine if you have a QPS. Okay, again, let's assume the number of queries that your search engine is getting is, let's say, 1000 queries per second. Let's assume. So this is a very nice example here. Again, it's important from a design standpoint. So let's assume you're getting 1000 queries per second. And let's assume the servers that you have, each of them, let's assume you have servers on which you've deployed your whole system. Each server can only answer 100 queries per second. Right? You can't do, I mean, each of these servers can't do more than 100. Okay, this is a pretty good server, let's say. Then what do you have to do? You have to run your Elasticsearch across multiple computers or across multiple nodes in a distributed system fashion. So this will capture 100 QPS, this will answer. So what happens is, think of it like a pipe that you get. Okay, you're getting 1000 queries per second from here. Now, here you can add something called as a load balancer. It's a very simple thing in distributed systems. What a load balancer does is, it keeps getting 1000 queries per second, right? Randomly, given any query, it will send 10% of the queries here. It will send 10% of the queries here, and so on and so forth. Oh, it's already 8 p.m. I'll finish this concept and I'll take Q&A. Okay. So finally, you have system 10, which also has 100 QPS. So what a load balancer does internally is, again, load balancer also uses a very simple hashing technique. Okay, given all the queries, search queries that you're getting, it will randomly hash them, and it'll randomly push it to each of these servers such that 10% of the queries go to this server, 10% of the queries go to this server, and so on and so forth. And remember that since our QPS is 1000 queries per second, we know each server can comfortably handle 100 QPS, right? Each server can handle 100 QPS, right? So you can just place a load balancer and distribute the load. Load balancer distributes the load. It's a very simple mechanism. Actually, there are publicly available open source load balancers that are fairly interesting and complex, but you can implement one yourself. It's not rocket science, at least a basic version of it. Now imagine your Elasticsearch has to run on all these 10 boxes, right? Which means you need a distributed inverted index system. Again, building a distributed inverted index system is not trivial. Okay, you need to know a lot of distributed computing. You need to know how to do sharding, a bunch of concepts. Even though you don't know some of these concepts in depth, Elasticsearch provides you all of that in an open source implementation. And it can do real-time queries. Which again, remember, we want our system to be very fast, right? And Elasticsearch is designed for something like this. Remember that Elasticsearch is used by some of the largest internet companies in the world. Okay, not Google for sure, but there are a lot of large e-commerce companies, large media companies which use Elasticsearch internally for many of their product search, for their movie search and things like that, right? So it's extremely popular. Okay. Now, okay, given that, how does our whole system work? Let's look at it. Okay, okay, probably it's already 8 o'clock, so I'll stop here. We'll continue from here on why we will use, because there are multiple architectures that I wanted to explain you here. But just remember that we'll be using Elasticsearch for the solution. Tomorrow, I'll explain how the whole system works in a very high level. Then we'll go into keyword-based search and semantic similarity. We'll learn about sentence vectors. What is the intuition behind, the mathematics behind sentence vectors? Again, this is primarily for those software engineers who may not know machine learning. I wanted to give you an intuitive understanding. Again, some mathematics, then there's a bunch of code. Okay, so there is a lot of, again, a modified design. How can you containerize this? All of that stuff. Again, please understand that we could not cover everything today. But one important takeaway right now is the importance of data structures for software engineers and machine learning roles. Many people ask me, hey, all this is cool, but why should I study data structures? Why am I being asked data structure questions for software engineer and machine learning roles? Because if you don't, again, this is a real world problem. If you're an engineer at Stack Overflow, or if you're part of the search team at Stack Overflow, you'll be building some of these things. And you need to know the basic data structures that we have used. You need to know what is hashing. You need to know how sets work. You need to know time complexity, right? So sounds good. So one more very important thing here is we will try and finish this today. Today anyway, the session is over. I'll do Q&A right now for the next 25 minutes or so. Tomorrow, which is the Sunday, most likely we should be able to finish this in 2 sessions. If we cannot finish this in 2 sessions, instead of rushing through it, we will continue and also take one more day to finish all of it. Because I have a lot of code that I want to walk you through, a lot of setup stuff, a lot of details that I want to walk you through. If it takes more time, that's okay. Instead of 2 sessions, we'll conduct more sessions, right? Sounds good. So let's go to the Q&A now. Okay, sounds good. Okay, so please ask your questions. I'll try to answer as many as I can, right? Yes, somebody says, okay, let's look at the questions here. How does TF-IDF ignore or give less importance for some common keys? Again, for that, you'll have to understand the mathematics behind TF-IDF. Again, you can just Google search for it and it should be simple for you to figure it out. It's not rocket science. It should be straightforward and you'll be able to understand it, right? So again, any questions you have, please put it in the chat window here. I'll try to answer as many as I can, all right? Before developing the inverted index, shouldn't we remove stop words so that we get more relevant results? Not always, Vishal. So that's a good question. So let me do one thing. Let me pop this out, pop chat. Let me make a full screen of this and answer the questions. Okay. Let me just zoom in so that everybody can see the questions also here. Okay. So Vishal has this question, which is before developing the inverted index, shouldn't we remove the stop words to get more relevant results? Again, removing the stop words may not always be the right approach because we'll be using sentence vectors where we are trying to convert the whole sentence into a numeric vector where some of the stop words are also important, like what, how, is. All these are stop words which play an important role when we also use sentence vectors. You don't have to explicitly do it yourself because TF-IDF will take care of giving less importance to stop words automatically. Okay. Okay. Can we use Dask data frame? You can use Dask data frames. They're certainly better than standard pandas data frame. But why do you want to again create something more complex? Simple CSV will do your job. Right? The code that I've shown you, right? The simple CSV code, this will solve your problem. Right? So where is our so simple CSV, right? CSV is anyway there. It's part of Python, works very well. It takes care of all the disk IO very efficiently. So you don't have to worry about the details there. You can use more complex solutions like Dask, but always remember simpler solutions, well-tested solutions are better than complex solutions. Okay. What about memory consumption? Very good question, Aniket. Yes. So this is a trade-off. Very good question that you asked. Since you raised the question, this is a typical trade-off between memory and speed. Remember that, again, I'll show you when we actually build the whole hash table for a few 100,000 questions. I'll show you that you can actually fit this whole thing into a modern desktop. I'll actually fit the whole thing into, I think, 4 GB of RAM. Almost 200,000 questions in Elasticsearch, you can fit them in 4 GB of RAM. But again, if you do not use hash table, use something else so as to save on memory. Again, Elasticsearch does a lot of very interesting hacks to save on memory, like using bits to represent things. A lot of interesting stuff it tries to do. It is very optimal implementation. But you can't compromise on speed. Imagine instead of using hash table, you use some tree-based method, tree-based data structure, right? You're not saving too much on memory, but your speed will suffer. Speed is absolutely the most important thing because users will not wait for more than half a minute for this, right? Somebody is asking about AutoML. Again, let's keep the discussion to the topic that we're discussing now. I'll avoid general questions because there are students here for this specific topic. So the importance of deployment, again, most deployment in the real world is very simple, right? Of course, depending on the company you work for, there might be deployment and operations engineers who are experts at that, who use Kubernetes, Docker, all sorts of stuff. If you are working in a large company, you will have a dedicated DevOps or Ops team that will take care of some of that. But if you are working at a startup or a small team which may not have those resources, you will have to deploy it yourself. That's why I'll cover a little bit about deployment also using simple APIs. Again, we have done previous sessions on how to use Flask APIs and how to deploy on EC2 very easily. Again, Docker, I also want to explain Docker in this series, primarily because you'll understand how Docker is the most popular way. Docker along with Kubernetes is the most popular way that operations engineer today deploy state-of-the-art large-scale systems, right? So again, if you're working in a startup or if you're working in a small team, you will have to do the deployment yourself. But it's not rocket science. Again, I didn't know deployment early on. I picked up on the job. Okay. I had to set up a whole Spark cluster from scratch because we didn't have resources at some point. And I did it. I mean, this was at Amazon, not even in our startup. And it's not rocket science. We can build it. So somebody says, can we solve this kind of problem using knowledge graph? Yes, you can. But knowledge graph is an extremely highly misused term. Okay. Most of the times, problems like this, again, there are some problems where, especially in internet search, where knowledge graphs are used as an additional source of information. Look at this. We said we'll be using keyword-based search. Look at this. We are planning to do it using two things, right? Keyword-based, inverted index-based search using TF, IDF and things like that. Plus, we are trying to use some sentence vectors. These are the two things that we are using. A true production system at large companies uses other things in addition to it. One of the things it uses is some information from knowledge graphs. Or it also could use topic models, which says, okay, what is the topic this question is talking about? Is it talking about Python? Is it talking about Java? Is it talking about something else? Right? So keyword-based search and sentence vectors are the two aspects that we are going to focus in this series. But there are other aspects also, whether it is topic models. Again, we can get topic models without having to construct them for our problem using the tags. You can also construct knowledge graph, but remember, knowledge graph is an extremely hyped up term. You have to be very careful to define your knowledge graph very carefully. Okay. Somebody says machine learning or data science. Again, sorry, I'll keep the discussion to the point here. Okay. Sir, I have two documents. I have vectorized TF IDF. To find the similarity, should we take cosine similarity? Again, when you have TF IDF, cosine similarity is a very popular metric. Again, the right similarity is something that you have to experiment with. In some situations, cosine similarity certainly works well. You should also try Euclidean distance or Euclidean distance based similarity, right? So both of them will work well. Can we add this as a simple project in resume? No. This is not a project that you have done. So you can't add it in your resume. And if you do so, you're just cheating the interviewer. And if the interviewer figures this out with just a Google search, you are in danger. You should solve problems of your own and put it in resume. Please don't take the problem that is solved by someone else and put it in your resume, because it will hurt you. Can we use Go language to read and load data? You're most welcome to do it. Again, Elasticsearch can use any programming language of your choice. But the problem with a fancy language like Go is it may not have all the libraries required to compute sentence vectors. The reason we are doing the whole thing in Python is because you have TensorFlow, PyTorch, phenomenal libraries for deep learning that are available in Python, and hence we're doing it. If you choose to use a fancy language like Go, make sure it is simple, it is fast, and it is scalable. You have the libraries to do it. Okay, where were we? Sorry, I missed some of the questions. What if the same question has same meaning but not same words? Exactly, that's what semantic search will work. If you notice the topics that I have listed here at the very beginning, so we will talk about that in we'll talk about it in sentence vectors, which is a very standard way in natural language processing to capture semantic similarity. Okay, that's what I'll explain anyway in tomorrow's session. Okay. What is meaning of inverted index? Again, you can rewatch this video. It will be available on YouTube and you'll be able to understand it, right? How to take care of misspelling words? That's a very good question. Again, when in the production environment, you will encounter misspelling words. So one thing that is done in these cases is a spell check is often done. I mean, it's again a design choice. Very good question. So what you can do here is you can do a spell check, get the corrected words or correct the misspelled words and use it as part of your search. That's one approach you can do. Of course, if you take the misspelled word and do it, you may not find any documents that contain it, and hence you will end up ignoring the whole thing. So it's always good to run a spell checker to correct some of these. And that's again, but remember that adding a spell checker might add more latency, more time into the whole ecosystem. It's a design choice, very important design choice, especially when you're building search at large scale. Can you show deployment of it in Heroku? I'll show the deployment of this on AWS on AWS EC2 to be precise. I'll show you how to deploy this whole solution in AWS EC2. That's the plan we have using simple Flask APIs. Again, you don't even require Flask APIs. You can just do it with AWS EC2. It's very simple to do it because Elasticsearch lets you do it over the internet very easily. Okay. Instead of taking cosine similarity with all selected questions, can we find most closest question, then list all questions which are similar to the closest question? Again, how do you do that? Okay, you have to pre-compute some things. Again, computing similar documents by using cosine similarity or any other similarity is a non-trivial problem. Okay, it is something that we'll discuss in tomorrow's session on how it can be done. There are also advanced algorithms. So I have a whole slide on a wide spectrum of algorithms. I have a whole slide of notes here. Where is this? Okay. So yeah. So how do you do nearest neighbor search from brute force to approximate nearest neighbors to KD trees to locality sensitive hashing to neighborhood graphs? There's a huge spectrum of algorithms that are there available at your disposal, right? So We'll see. We'll discuss some of them. We can't go into the depths of everything. Okay. Yeah, instead of TF-IDF, can we use TF-IDF word2vec? Again, the reason I explained TF-IDF concept is because it's the simplest, and Elasticsearch implicitly uses a TF-IDF based scheme. But you can override the scoring function to whatever you want. Don't worry about it. Yes, so this video will be available even after the live session, and you should be able to watch this video even after that. So will ML jobs increase after the pandemic? Again, I've done a session, a long 1 hour session explaining the impact of pandemic on machine learning jobs. It's there on our channel. Please check it. Difference between Redis and Elasticsearch. Again, they're completely two different things. Elasticsearch is an inverted index, right? Primarily meant for searching documents using TF-IDF based schemes and using sentence vectors. Redis is more like a distributed hash table, right? What is your typical hash table? Your typical hash table is basically keys and values. It is stored in one box, right? It's all stored in one box on your local box. But if you want a hash table that is distributed across multiple computers, because the whole hash table cannot fit in one box, that's when you go and use Redis, right? Redis is basically a distributed, scalable hash table. Elasticsearch is a distributed inverted index. They're two different things. Okay. For deployment, I recommend using Fast API, ASGI. Again, I'm not a big fan of fancy frameworks. I mean, of course, everybody has their priorities. There are hundreds of frameworks that you have to deploy things. I try to explain concepts from first principles. Imagine you have an EC2 box, which is a simple server that you have on your on some cloud-based system like AWS. How do you deploy it using this? Again, we want to be as framework neutral as possible. So all we are trying to do is we're trying to explain you the foundations here, because frameworks come and go. You learn some, you'll forget some, but foundational knowledge is the most important concept here, right? Yes, can I showcase this ML project with some updates? Again, please make sure that you do considerable amount of changes before you put it as your project. Okay, I'll suggest you some edits, some extensions to this. That's very welcome, right? For example, I've mentioned this, right? So if you go here at the end of this whole series, I'll touch upon how to extend this, how to scale it, and I'll give you some optional assignments. You can complete those and focus on those when you try to showcase this project via a blog or via on your resume, right? So that's always welcome. So somebody says, I saw KD tree written over there. Yes. So I will show you that KD tree is not what is actually used, but I wanted to give you an overview on what type of data structures can be used to solve a problem like this. We will not end up using KD trees. We'll use some hashing based technique eventually. Are you going to do exploration about Docker? Yes. So if you look at some of the notes that I have, I wanted to show you how to install Docker. Okay, I wanted to explain you about why we need containerization from a developer testing and deployment perspective. Again, there's a nice diagram about from docker.com itself about how containers are different from virtual machines and how can you mix both of them, how to install Docker on your desktop, then how to set up Docker for this exact instance, bunch of Docker commands to set up Docker with Elasticsearch. Then, so all that is what I have planned for. So I'll cover that. New version of ES allows storage of vectors also. Yes, we will use that. Okay. Sounds good, folks. Okay, we have 10 more minutes, so I can take a few more questions if you have. So I can take some more questions. I think, again, I'll avoid general purpose questions because here we want to discuss specifically about this problem, which is Q&A search engine. So let's focus on that. Is there something that I've missed that students have asked or participants have asked earlier? Again, I'm trying to answer as many questions as I can. I might miss one or two of them here. Okay, so since I think I've answered all the questions, all the last 20-30 questions, at least more than that. What are the most important data structures one must know? It's a very good question, Abhijit. You should certainly know hashing. You should certainly know lists, sets, a little bit about trees. I think that's good enough. Those are, again, a little bit about graphs also will help, right? So I think those are the basic data structures that are also covered at undergraduate level. Okay. Okay. Same meaning, not same words. I talked about that semantic similarity. Okay, I think I've answered. Oh, good question. I forgot this. Elasticsearch has limits to return maximum 10K results. What if our search result has from Elastic is 20 to 50K documents? Again, the reason Elasticsearch has some limit, I think you can certainly change this by going into the settings of Elasticsearch. But the reason Elasticsearch limits the number of search results is nobody is going to read through the 10,000th search result. Nobody even goes through after 5 or 6 search results. I think the top 10 are the most important. Nobody even goes to the next one. That's why Elasticsearch limits it to 10,000, some number. I don't know this number by heart, but I think it certainly limits the number of results to a certain number. You can always change it by changing your query. Okay. What kind of search algorithms on high level does Google use? Google certainly uses inverted indices, without doubt. So Google has, okay, let me explain that. Google uses inverted indices. It certainly uses, again, imagine Google's scale of inverted indices is going to be crazy. Google, I'm sure, does not use Elasticsearch. They have built their own stuff that scales. And of course, it uses keyword-based stuff along with inverted indices, TF-IDF based stuff. I'm sure it uses a lot of deep learning based stuff like sentence vectors. It is public knowledge that Google almost uses 800 such small algorithms which run parallelly, right? Each of them have their own data structures so as to give you the best results. Again, Google also has to take care of abusive posts, all sorts of things, right? So it is believed that Google uses almost 800 such algorithms, like using sentence vectors, using TF-IDF, using something like BERT, using some other algorithms. It is believed that a large number of Google algorithms are deep learning based, but it has almost 800 such algorithms and data structures that it uses. But I'm sure it uses inverted indices at its very core, without doubt. I'm sure it uses TF-IDF and sentence vectors also. But there could be many other systems that it uses, like knowledge graphs that it built, tons of other sources of data that it has, right? So Solr, again, Solr, Lucene, Elasticsearch, there are 3 popular. Solr, I remember Solr being used in around 2007-ish, right? Solr is also an open source. So Solr is also an open source inverted indices based implementation, very popular. Then came something called Lucene, Lucene, and Elasticsearch is built on Lucene, right? So think of them as, again, I remember Yahoo search at some point of time. I'm sure they don't use it today. At some point of time, for some of the Yahoo search functionality, not all, for some of the functionality, they were using Solr. It's also an open source project from the early 2000s. What is Kibana? Again, there is this whole stack called as, okay, let me show you that. So if you go to, okay, so if you go here, Elasticsearch has, so you have 3 things, Elasticsearch, Kibana, and Logstash, right? So if you go to Kibana, okay, let me go here, okay. So Kibana basically gives you a visual interface, right? It gives you a very nice visual interface to be able to crunch through. Again, Elasticsearch is the core backend. What Kibana does, as you can see here, it gives you a free and open source interface that helps you visualize the data that is there in Elasticsearch. So Kibana, think of it like a simple way to build visualizations on top of Elasticsearch data. Then you also have Logstash, right? So where is Logstash? These 3 are tightly related. They all 3 have been developed together and things like that. So Logstash, on the other hand, helps you fetch data from multiple sources and inject and transform them and put them into your Elasticsearch ecosystem, right? So Logstash is a free and open source server-side data processing pipeline. Again, what I just told you, right? So Logstash, again, Kibana, Logstash, and Elasticsearch are often used together, very often, but you do not always use it, right? So we will not focus on Logstash and Kibana. We'll mostly focus on Elasticsearch itself. Yes, so Apache Lucene is, again, I know for sure that Elasticsearch is built on Lucene. I don't recall the relationship between Solar and Lucene, but it should be easy to Google it up. Any suggestions to installing Docker in Windows? It's actually very simple. You can try it. I have a link here. Just type Docker install Windows. So there is something called as Docker Desktop, right? So Docker Desktop is a nice, so I'll show you my Docker Desktop dashboard. So this is the Docker Desktop that I have. It's a simple UI based system. I have something called My Elastic, which is running on my computer right now. This is the Mac version, but it's very simple. You can just download this Docker Desktop and install it. You get Docker on your Windows box. It's extremely simple. I've done exactly the same thing on Mac. On Linux, you just have to execute some commands, but somebody who's using Linux, I'm sure can figure out how to do it. I'll also provide links when we discuss Docker tomorrow. Can we use Beam Search and BlueScore? Again, you can use it, but the problem here is, but it doesn't support Windows 10 Home. Actually, I didn't know this. Okay, so I didn't know that. Oh, you're asking about Windows Home Edition. Actually, I don't know. I don't know about Windows Home Edition because I don't have it. Again, I don't have a Windows box myself. I don't know how to install Docker on Windows Home. Okay, one second. Oh, there is this. Sorry. Install Docker Desktop on Windows Home. There is a blog. Yeah. So look at this. Install Docker Desktop on Windows Home. It seems possible. I think there is some variation that you have to do. You have to modify a bunch of things, but it should be possible. Right? It's not impossible. I'm sure people who built Docker thought through that, because some of you may have Windows Home Edition and not Professional Edition, right? But there is this blog. Just a Google search away, right? Sorry, somebody is asking about Beam Search and BlueScore. Again, you can use any scoring function of your choice, but how will you use Blue Search? You can use Beam Search also, but then I think it is not easy to use it in the context of Elasticsearch itself, right? You will have to implement everything from scratch, which is quite time taking from a production perspective. But if you want to do this as a project, certainly you can implement Beam Search from scratch and see and compare how Beam Search algorithm works as compared to what Elasticsearch works, right? Is EDA will help Stack Overflow data to understand this problem? Yes. So I've not done much EDA here because the focus here is about high level design and implementing something quickly. But if you have time, please do perform EDA, and you can get EDA for this problem very easily. So if you just go to, again, a lot of people have done some EDA for this. For example, if you do, what is this? This is Kaggle, Stack Overflow. Okay, Stack Overflow. Okay, Stack Sample. Yeah. So if you go to this, if you look at the kernels here, you get a lot of kernels here where people have done some exploratory data analysis. You can just read up this so as to get a good understanding of what people are saying, right? So this is certainly one way of doing it. You can also do your own EDA to understand the data better, right? Okay. Sorry, question answering. Identify the questions to, okay, about Wikipedia page content. So, okay, so this is a different question that you're answering, right? So, so for example, if you want to do so for example, imagine you have this, right? So this question is different, Praneeth. It's slightly different from what we're trying to solve. So the question that you have here is, you have a Wikipedia page, right? You have a Wikipedia page and you have a question, right? So using this Wikipedia page and using this question, you want to find the answer. You want to find the answer based on this Wikipedia page or Wikipedia content, right? Some page. Let's assume this page is about nearest neighbor search, and there is some question about nearest neighbor search, right? So your model takes the question and this document, and it has to generate the answer. So we've already done a live session exactly doing this using BERT. So we have in our BERT series of live sessions, I think there are 2 or 3 live sessions there. In one of the sessions, we said, how do you fine tune BERT for a question answering task? We have done a live session and a code walkthrough, actually line by line code walkthrough, where it's exactly the same thing. You have a question and you have the Wikipedia data and you have to generate the answer by fine tuning BERT for Q&A tasks. That's a different problem as compared to this, right? So yeah, can we implement this Q&A on a MOOC platform? Yes, you can implement it if you have data. Okay, we're actually using Elasticsearch and sentence vectors to build something for our own students now. Okay, so again, you can use any ranking function of your choice. Okay, what I explained to you a while ago is the default scoring function that is there in Elasticsearch, which is based on TF-IDF. But we'll see in some of our examples later that instead of using the TF-IDF based thing, we'll use cosine similarity. So you can implement any scoring function of your choice. Elasticsearch is very extendable, and you can make it work with any scoring function of your choice. Okay. Will it work for multi-language? Yes, it also works for multilingual data. A lot of Elasticsearch is also used for a lot of non-English languages, both in Europe and Southeast Asia. So it works even for, and again, the sentence vectors are also designed for almost all the major languages which are widely spoken. So you can make whatever approach we're discussing, you can extend it to multiple languages as long as you have good sentence vector models for them, and as long as the languages follow the basic rules, right? So okay, sounds good. Sounds good. Thank you very much, folks. It's already 8:32, so I'll stop the session today. And as I mentioned, we'll try and finish Saturday. We have done a 1.5 hour session. I hope I've answered. Again, we've almost spent 30 minutes answering questions. So tomorrow we'll do the same thing, 60 plus 30. And if you cannot finish, I don't think we can finish in tomorrow's session. Looking at the speed at which we are going, we'll follow the same format. If you can't finish it, we'll also extend it to Monday. Whatever time it takes, I want to go in detail so that even students who are in beginner sections, some students or learners who may not know machine learning or who may not know system design can still understand it step by step. Okay, sounds good, folks. Thank you very much.